Current, electricity. Electric current. Imagine a small area held normal to the direction of flow of charges. Both the positive and the negative charges may flow forward and backward across the area. In a given time interval t, let q plus be the net amount, that is forward minus backward, of positive charge that flows in the forward direction across the area. Similarly, let q minus be the net amount of negative charge flowing across the area in the forward direction. The net amount of charge flowing across the area in the forward direction in the time interval t then is q is equal to q plus minus q minus. This is proportional to T for steady current and the quotient. I is equal to Q upon T. Equation 1 is defined to be the current across the area in the forward direction. If it turns out to be a negative number, it implies a current in the backward direction. Currents are not always steady, and hence more generally, we define the current as follows. Let delta Q be the net charge flowing across a cross-section of a conductor during the time interval delta t, that is between times t and t plus delta t. Then the current at time t across the cross-section of the conductor is defined as the value of the ratio of delta q to delta t in the limit of delta t tending to 0. I of t is equal to limit delta t tends to 0, delta q upon delta t, equation 2. In SI units, the unit of current is ampere. An ampere is typically the order of magnitude of currents in domestic appliances. An average lightning carries currents of the order of tens of thousands of amperes, and at the other extreme, currents in our nerves are in microamperes. Electric currents in conductors. An electric charge will experience a force if an electric field is applied. If it is free to move, it will thus move, contributing to a current. In nature, free charged particles do exist like in upper strata of atmosphere called the ionosphere. However, in atoms and molecules, the negatively charged electrons and the positively charged nuclei are bound to each other and are thus not free to move. Bulk matter is made up of many molecules. A gram of water, for example, contains approximately 10 raised to 22 molecules. These molecules are so closely packed that the electrons are no longer attached to individual nuclei. In some materials, the electrons will still be bound. That is, they will not accelerate even if an electric field is applied. In other materials, notably metals, some of the electrons are partially free to move within the bulk material. These materials, generally called conductors, develop electric currents in them when an electric field is applied. If we consider solid conductors, then of course the atoms are tightly bound to each other so that the current is carried by the negatively charged electrons. There are, however, other types of conductors like electrolytic solutions where positive and negative charges both can move. In our discussions, we will focus only on solid conductors so that the current is carried by the negatively charged electrons in the background of fixed positive ions. Consider first the case when no electric field is present. The electrons will be moving due to thermal motion during which they collide with the fixed ions, an electron colliding with an ion emerges with the same speed as before the collision. However, the direction of its velocity after the collision is completely random. At a given time, there is no preferential direction for the velocities of the electrons. Thus, on the average, the number of electrons traveling in any direction will be equal to the number of electrons traveling in the opposite direction. So, there will be no net electric current. Let us now see what happens to such a piece of conductor if an electric field is applied. To focus our thoughts, imagine the conductor in the shape of a cylinder of radius r. Suppose we now take two thin circular discs of a dielectric of the same radius and put positive charge plus q distributed over one disc and similarly minus q at the other disc. We attach the two discs on the two flat surfaces of the cylinder. An electric field will be created and is directed from the positive towards the negative charge. The electrons will be accelerated due to this field towards plus q. They will thus move to neutralize the charges. The electrons, as long as they are moving, will constitute an electric current. Hence, in the situation considered, there will be a current for a very short while and no current thereafter. We can also imagine a mechanism where the ends of the cylinder are supplied with fresh charges to make up for any charges neutralized by electrons moving inside the conductor. In that case, there will be a steady electric field in the body of the conductor. This will result in a continuous current rather than a current for a short period of time. Mechanisms which maintain a steady electric field are cells or batteries. Ohm's law, a basic law regarding flow of currents, was discovered by G.S. Ohm in 1828. Long before the physical mechanism responsible for flow of currents was discovered. Imagine a conductor through which a current I is flowing and let V be the potential difference between the ends of the conductor. Then Ohm's law states that V is proportional to I, or V is equal to Ri, equation 3, where the constant of proportionality R is called the resistance of the conductor. The SI units of resistance is ohm and is denoted by the symbol ohm. The resistance R not only depends on the material of the conductor but also on the dimensions of the conductor. The dependence of R on the dimensions of the conductor can easily be determined as follows. Consider a conductor satisfying equation 3 to be in the form of a slab of length L and cross-sectional area A. Imagine placing two such identical slabs side by side so that the length of the combination is 2L. The current flowing through the combination is the same as that flowing through either of the slabs. If V is the potential difference across the ends of the first slab, then V is also the potential difference across the ends of the second slab. Since the second slab is identical to the first and the same current I flows through both, the potential difference across the ends of the combination is clearly sum of the potential difference across the two individual slabs and hence equals 2V. The current through the combination is I and the resistance of the combination RC is equal to 2V upon I is equal to 2R, equation 4. Since V upon I is equal to R, the resistance of either of the slabs. Thus, doubling the length of a conductor doubles the resistance. In general, then resistance is proportional to length. R is proportional to L. Equation 5. Next, imagine dividing the slab into 2 by cutting it lengthwise so that the slab can be considered as a combination of two identical slabs of length L, but each having a cross-sectional area of A upon 2. For a given voltage V across the slab, if I is the current through the entire slab, then clearly the current flowing through each of the two half slabs is I upon 2, since the potential difference across the ends of the half slabs is V. That is the same as across the full slab. The resistance of each of the half slabs R1 is equal to V upon I upon 2 is equal to 2V upon I is equal to 2R. Equation 6. Thus, having the area of the cross section of a conductor doubles the resistance. In general, then the resistance R is inversely proportional to the cross-sectional area. R is proportional to 1 upon A. Equation 7. Combining equations 5 and 7, we have R is proportional to L upon A. Equation 8. And hence, for a given conductor, R is equal to rho L upon A. Equation 9. Where the constant of proportionality rho depends on the material of the conductor, but not on its dimensions. Rho is called resistivity. Using the last equation, Ohm's law reads V is equal to I into R is equal to I rho L upon A. Equation 10. Current per unit area taken normal to the current I upon A is called current density and is denoted by J. The SI units of the current density are ampere per meter square. Further, if E is the magnitude of uniform electric field in the conductor whose length is L, then the potential difference V across its ends is EL. Using this, the last equation reads EL is equal to J rho L or E is equal to J rho. Equation 11. The above relation for magnitudes E and J can indeed be cast in a vector form. The current density, which we have defined as the current through unit area normal to the current, is also directed along E and is also a vector J is equivalent to J E upon A. Thus, the last equation can be written as E is equal to J rho, equation 12, or J is equal to sigma E, equation 13, where sigma is equivalent to L upon rho is called the conductivity. Ohm's law is often stated in an equivalent form, equation 13, in addition to equation 3. Drift of electrons and the origin of resistivity. An electron will suffer collisions with the heavy fixed ions, but after collision, it will emerge with the same speed but in random directions. If we consider all the electrons, their average velocity will be 0, since their directions are random. Thus, if there are n electrons and the velocity of the ith electron I is equal to 1, 2, 3 up to n at a given time is Vi, then 1 upon n summation from I equal to 1 to n Vi is equal to 0. Equation 14. Consider now the situation when an electric field is present. Electrons will be accelerated due to this field by A is equal to minus E into E upon M. Equation 15. Where minus E is the charge and m is the mass of an electron. Consider again the ith electron at a given time t. This electron would have had its last collision some time before t, and let ti be the time elapsed after its last collision. If vi was its velocity immediately after the last collision, then its velocity vi at time t is vi is equal to vi minus e into e upon m into ti, equation 16. Since starting with its last collision, it was accelerated with an acceleration given by equation 15 for a time interval ti. The average velocity of the electrons at time t is the average of all the vi's. The average of vi's is 0. Since immediately after any collision, the direction of the velocity of an electron is completely random. The collisions of the electrons do not occur at regular intervals but at random times. Let us denote by τ the average time between successive collisions. Then at a given time, some of the electrons would have spent time more than τ and some less than τ. In other words, the time ti will be less than τ for some and more than τ for others. As we go through the values of I is equal to 1, 2 up to n. The average value of ti then is τ, known as relaxation time. Thus, averaging equation 16 over the n electrons at any given time t gives us for the average velocity Vd. Vd is equal to Vi average is equal to Vi average minus E into E upon m into Ti average is equal to 0 minus E into E upon m into τ is equal to minus E into E upon m into τ, equation 17. This last result is surprising. It tells us that the electrons move with an average velocity which is independent of time, although electrons are accelerated. This is the phenomenon of drift, and the velocity Vd in equation 17 is called the drift velocity. Because of the drift, there will be net transport of charges across any area perpendicular to E. Consider a planar area A located inside the conductor such that the normal to the area is parallel to E. Then, because of the drift, in an infinitesimal amount of time delta t, all electrons to the left of the area at distances up to mod of Vd into delta t would have crossed the area. If n is the number of free electrons per unit volume in the metal, then there are n into delta t into mod of Vd into A such electrons. Since each electron carries a charge minus E, the total charge transported across this area A to the right in time delta t is minus Ne into A into mod of Vd into delta t. E is directed towards the left and hence the total charge transported along E across the area is negative of this. The amount of charge crossing the area A in time delta t is I into delta t, where I is the magnitude of the current. Hence, I into delta t is equal to plus Ne into A into mod of Vd into delta t, equation 18. Substituting the value of mod of Vd from equation 17, I into delta t is equal to E square A upon m tau n into delta t into mod of E, equation 19. By definition, I is related to the magnitude mod of J of the current density by I is equal to mod of J into A, equation 20. Hence, from equations 19 and 20, mode of J is equal to NE square upon M into tau into mode of E. Equation 21. The vector J is parallel to E, and hence we can write equation 21 in the vector form. J is equal to NE square upon M tau into E. Equation 22. Comparison with equation 13, J is equal to sigma E, shows that equation 22 is exactly the Ohm's law. If we identify the conductivity sigma as sigma is equal to NE square upon M tau, equation 23, we thus see that a very simple picture of electrical conduction reproduces Ohm's law. We have, of course, made assumptions that tau and n are constants, independent of. Example 1a. Estimate the average drift speed of conduction electrons in a copper wire of cross-sectional area 1.0 into 10 raised to minus 7 meter square, carrying a current of 1.5 ampere. Assume that each copper atom contributes roughly 1 conduction electron. The density of copper is 9.0 into 10 cube kilogram per meter cube, and its atomic mass is 63.5 unit. B. Compare the drift speed obtained above with number 1. Thermal speeds of copper atoms at ordinary temperatures. Number 2. Speed of propagation of electric field along the conductor which causes the drift motion. Solution. A. The direction of drift velocity of conduction electrons is opposite to the electric field direction. That is, electrons drift in the direction of increasing potential. The drift speed Vd is given by Vd is equal to I upon NEA. Now, E is equal to 1.6 into 10 raised to minus 19 coulomb. A is equal to 1.0 into 10 raised to minus 7 meter square. I is equal to 1.5 ampere. The density of conduction electrons N is equal to the number of atoms per cubic meter. Assuming 1 conduction electron per copper atom S is reasonable from its valence electron count of 1. A cubic meter of copper has a mass of 9.0 into 10 cube kilogram. Since 6.0 into 10 raised to 23 copper atoms have a mass of 63.5 gram, N is equal to 6.0 into 10 raised to 23 upon 63.5 into 9 into 10 raised to 6 is equal to 8.5 into 10 raised to 28 meter raised to minus 3, which gives Vd is equal to 1.5 upon 8.5 into 10 raised to 28 into 1.6 into 10 raised to minus 19 into 1.0 into 10 raised to minus 7 is equal to 1.1 into 10 raised to minus 3 meter per second is equal to 1.1 millimeter per second. B. Number 1. At a temperature T, the thermal speed of a copper atom of mass m is obtained from average value of 1 upon 2 mv square is equal to 3 upon 2 kBt and is thus typically of the order of square root of kBt upon m, where kb is the Boltzmann constant. For copper at 300 Kelvin, this is about 2 into 10 square meter per second. This figure indicates the random vibrational speeds of copper atoms in a conductor. Note that the drift speed of electrons is much smaller, about 10 raised to minus 5 times the typical thermal speed at ordinary temperatures. Number 2. An electric field traveling along the conductor has a speed of an electromagnetic wave. namely equal to 3.0 into 10 raised to 8 meter per second. The drift speed is, in comparison, extremely small, smaller by a factor of 10 raised to minus 11. Example 2. A. In example 1, the electron drift speed is estimated to be only a few millimeter per second for currents in the range of a few amperes. How then is current established almost the instant a circuit is closed? B. The electron drift arises due to the force experienced by electrons in the electric field inside the conductor. But force should cause acceleration. Why then do the electrons acquire a steady average drift speed? See, if the electron drift speed is so small and the electron's charge is small, how can we still obtain large amounts of current in a conductor? D. When electrons drift in a metal from lower to higher potential, does it mean that all the free electrons of the metal are moving in the same direction? E. Are the paths of electrons straight lines between successive collisions with the positive ions of the metal in the number 1. Absence of electric field, number 2. Presence of electric field? Solution. A. Electric field is established throughout the circuit almost instantly with the speed of light, causing at every point a local electron drift. Establishment of a current does not have to wait for electrons from one end of the conductor traveling to the other end. However, it does take a little while for the current to reach its steady value. B. Each free electron does accelerate, increasing its drift speed until it collides with a positive ion of the metal. It loses its drift speed after collision but starts to accelerate and increases its drift speed again only to suffer a collision again and so on. On the average, therefore, electrons acquire only a drift speed. C. Simple, because the electron number density is enormous, is similar to 10 raised to 29 meter raised to minus 3. D. By no means, the drift velocity is superposed over the large random velocities of electrons. E. In the absence of electric field, the paths are straight lines. In the presence of electric field, the paths are, in general, curved. Mobility. As we have seen, conductivity arises from mobile charge carriers. In metals, these mobile charge carriers are electrons. In an ionized gas, they are electrons and positive charged ions. In an electrolyte, these can be both positive and negative ions. An important quantity is the mobility mu, defined as the magnitude of the drift velocity per unit electric field. Mu is equal to mod of Vd upon E, equation 24. The SI unit of mobility is meter square per volt into second and is 10 raised to 4 of the mobility in practical units, centimeter square per volt into second. Mobility is positive. We have Vd is equal to E to E upon m. Hence, mu is equal to Vd upon E is equal to E to upon m, equation 25, where tau is the average collision time for electrons. Limitations of Ohm's law. Although Ohm's law has been found valid over a large class of materials, there do exist materials and devices used in electric circuits where the proportionality of V and I does not hold. The deviations broadly are one or more of the following types. A. V ceases to be proportional to I. B. The relation between V and I depends on the sign of V. In other words, if I is the current for a certain V, then reversing the direction of V, keeping its magnitude fixed, does not produce a current of the same magnitude as I in the opposite direction. This happens, for example, in a diode. C. The relation between V and I is not unique. That is, there is more than one value of V for the same current I. A material exhibiting such behavior is gallium arsenide. Materials and devices not obeying Ohm's law in the form of equation 3 are actually widely used in electronic circuits. Resistivity of various materials. The resistivities of various common materials are listed in table. The materials are classified as conductors, semiconductors, and insulators depending on their resistivities in an increasing order of their values. Metals have low resistivities in the range of 10⁻⁸ ohm into meter to 10⁻⁶ ohm into meter. At the other end are insulators like ceramic, rubber, and plastics having resistivities 10⁻18 times greater than metals or more. In between the two are the semiconductors. These, however, have resistivities characteristically decreasing with a rise in temperature. The resistivities of semiconductors are also affected by presence of small amount of impurities. This last feature is exploited in use of semiconductors for electronic devices. Resistivities of some materials. Material resistivity ρ ohm into meter at 0 degrees Celsius. Temperature coefficient of resistivity alpha degree Celsius raised to -1 1 upon rho d rho upon dt at 0 degree Celsius. Conductors. Material silver resistivity 1.6 into 10⁻⁸. Temperature coefficient of resistivity 0.0041. Material copper resistivity 1.7 into 10⁻⁸. Temperature coefficient of resistivity 0.0068. Material aluminium resistivity 2.7 into 10⁻⁸. Temperature coefficient of resistivity 0.0043. Material tungsten resistivity 5.6 into 10⁻⁸. Temperature coefficient of resistivity 0.0045. Material iron resistivity 10 into 10⁻⁸. Temperature coefficient of resistivity 0.0065. Material platinum resistivity 11 into 10⁻⁸. Temperature coefficient of resistivity 0.0039. Material mercury resistivity 98 into 10⁻⁸. Temperature coefficient of resistivity 0.0009. Material nichrome alloy of nickel, iron, chromium. Resistivity approximately equal to 100 into 10⁻⁸. Temperature coefficient of resistivity 0.0004. Material manganese alloy resistivity 48 into 10⁻⁸. Temperature coefficient of resistivity 0.002 into 10⁻⁻3. Semiconductors Material carbon, graphite. Resistivity 3.5 into 10 raised to minus 5. Temperature coefficient of resistivity minus 0.0005. Material germanium. Resistivity 0.46. Temperature coefficient of resistivity minus 0.05. Material silicon. Resistivity 2300. Temperature coefficient of resistivity minus 0.07. Insulators. Material pure water. Resistivity 2.5 into 10 raised to 5. Material glass. Resistivity 10 raised to 10 to 10 raised to 14. Material hard rubber. Resistivity 10 raised to 13 to 10 raised to 16. Material sodium chloride NaCl. Resistivity is approximately equal to 10 raised to 14. Material fused quartz. Resistivity is approximately equal to 10 raised to 16. Commercially produced resistors for domestic use or in laboratories are of two major types: wire-bound resistors and carbon resistors. Wire-bound resistors are made by winding the wires of an alloy, namely manganese, constantan, nichrome, or similar ones. The choice of these materials is dictated mostly by the fact that their resistivities are relatively insensitive to temperature. These resistances are typically in the range of a fraction of an ohm to a few hundred ohms. Resistors in the higher range are made mostly from carbon. Carbon resistors are compact, inexpensive, and thus find extensive use in electronic circuits. Carbon resistors are small in size and hence their values are given using a color code. Resistor color codes. Color, number, multiplier, tolerance. In percentage. Color black, number 0, multiplier 1. Color brown, number 1, multiplier 10 raised to 1. Color red, number 2, multiplier 10 square. Color orange, number 3, multiplier 10 cube. Color yellow, number 4, multiplier 10 raised to 4. Color green, number 5, multiplier 10 raised to 5. Color blue, number 6, multiplier 10 raised to 6. Color violet, number 7, multiplier 10 raised to 7. Color grey, number 8, multiplier 10 raised to 8. Color white, number 9, multiplier 10 raised to 9. Color gold, multiplier 10 raised to minus 1. Tolerance 5. Color silver, multiplier 10 raised to minus 2. Tolerance 10. Color no color, tolerance 20. The resistors have a set of coaxial colored rings on them, whose significance are listed in table. The first two bands from the end indicate the first two significant figures of the resistance in ohms. The third band indicates the decimal multiplier. The last band stands for tolerance of possible variation in percentage about the indicated values. Sometimes this last band is absent and that indicates a tolerance of 20%. For example, if the four colors are orange, blue, yellow, and gold, the resistance value is 36 into 10 raised to 4 ohm with a tolerance value of 5%. Temperature dependence of resistivity. The resistivity of a material is found to be dependent on the temperature. different materials do not exhibit the same dependence on temperatures over a limited range of temperatures that is not too large. The resistivity of a metallic conductor is approximately given by rho T is equal to rho 0 into 1 plus alpha T minus T0. Equation 26, where rho T is the resistivity at a temperature T and rho 0 is the resistivity at a reference temperature T0. Alpha is called the temperature coefficient of resistivity, and from equation 26, the dimension of alpha is temperature raised to -1. For metals, alpha is positive and values of alpha for some metals at T0 is equal to 0 degree Celsius are listed in table. The relation of equation 26 implies that a graph of rho T plotted against T would be a straight line. At temperatures much lower than 0 degree Celsius, the graph, however, deviates considerably from a straight line. Equation 26 thus can be used approximately over a limited range of T around any reference temperature T0, where the graph can be approximated as a straight line. Some materials like nichrome, which is an alloy of nickel, iron and chromium, exhibit a very weak dependence of resistivity with temperature. Manganese and constantan have similar properties. These materials are thus widely used in wire-bound standard resistors since their resistance values would change very little with temperatures. Unlike metals, the resistivities of semiconductors decrease with increasing temperatures. A typical dependence is shown in figure. We can qualitatively understand the temperature dependence of resistivity in the light of our derivation of equation 23. From this equation, resistivity of a material is given by rho is equal to 1 upon sigma is equal to m upon Ne square tau. Equation 27. Rho thus depends inversely both on the number n of free electrons per unit volume and on the average time tau between collisions. As we increase temperature, average speed of the electrons, which act as the carriers of current, increases, resulting in more frequent collisions. The average time of collisions, tau, thus decreases with temperature. In a metal, N is not dependent on temperature to any appreciable extent, and thus the decrease in the value of tau with rise in temperature causes rho to increase. For insulators and semiconductors, however, N increases with temperature. This increase more than compensates any decrease in tau in equation 23, so that for such materials, rho decreases with temperature. Example 3. An electric toaster uses nichrome for its heating element. When a negligibly small current passes through it, its resistance at room temperature 27.0 degrees Celsius is found to be 75.3 ohm. When the toaster is connected to a 230 volt supply, the current settles after a few seconds to a steady value of 2.68 ampere. What is the steady temperature of the nichrome element? The temperature coefficient of resistance of nichrome averaged over the temperature range involved is 1.70 into 10 raised to minus 4 per degree Celsius. Solution: when the current through the element is very small, heating effects can be ignored and the temperature T1 of the element is the same as room temperature. When the toaster is connected to the supply, its initial current will be slightly higher than its steady value of 2.68 ampere. But due to heating effect of the current, the temperature will rise. This will cause an increase in resistance and a slight decrease in current. In a few seconds, a steady state will be reached when temperature will rise no further and both the resistance of the element and the current drawn will achieve steady values. The resistance R2 at the steady temperature T2 is R is equal to V upon I. R2 is equal to 230 volt upon 2.68 ampere is equal to 85.8 ohm. Using the relation R2 is equal to R1 into 1 plus alpha T2 minus T1 with alpha is equal to 1.70 into 10 raised to minus 4 per degree Celsius. R2 upon R1 minus 1 is equal to alpha T2 minus T1. 1 upon alpha into R2 upon R1 minus 1 is equal to T2 minus T1. T2 minus T1 is equal to R2 minus R1 upon alpha into R1. T2 minus T1 is equal to 85.8 minus 75.3 upon 75.3 into 1.70 into 10 raised to minus 4. T2 minus T1 is equal to 820 degrees Celsius. That is, T2 is equal to T1 plus 820 degrees Celsius. T2 is equal to 820 plus 27.0 degrees Celsius is equal to 847 degrees Celsius. Thus, the steady temperature of the heating element is 847 degrees Celsius. Thus, the steady temperature of the heating element when heating effect due to the current equals heat loss to the surroundings is 847 degrees Celsius. Example 4. The resistance of the platinum wire of a platinum resistance thermometer at the ice point is 5 ohm and at steam point is 5.23 ohm. When the thermometer is inserted in a hot bath, the resistance of the platinum wire is 5.795 ohm. Calculate the temperature of the bath. Solution: R0 is equal to 5 ohm, R100 is equal to 5.23 ohm and RT is equal to 5.795 ohm. Now T is equal to RT minus R0 upon R100 minus R0 into 100. RT is equal to R0 into 1 plus alpha T is equal to 5.795 minus 5 upon 5.23 minus 5 into 100 is equal to 0.795 upon 0.23 into 100 is equal to 345.65 degrees Celsius. Electrical energy power. Consider a conductor with endpoints A and B, in which a current I is flowing from A to B. The electric potential at A and B are denoted by V of A and V of B respectively. Since current is flowing from A to B, V of A is greater than V of B, and the potential difference across AB is V is equal to V of A minus V of B is greater than 0. In a time interval delta t, an amount of charge delta q is equal to I into delta t travels from A to B. The potential energy of the charge at A was Q into V of A, and similarly at B, it is Q into V of B. Thus, change in its potential energy, delta U potential is equal to final potential energy minus initial potential energy is equal to delta Q into V of B minus V of A is equal to minus delta Q V is equal to minus I V delta T is less than 0. Equation 28. If charges moved without collisions through the conductor, their kinetic energy would also change so that the total energy is unchanged. Conservation of total energy would then imply that delta K is equal to minus delta U potential. Equation 29. That is, delta K is equal to I V delta T is greater than 0. Equation 30. Thus, in case charges were moving freely through the conductor under the action of electric field, their kinetic energy would increase as they move. However, seen earlier that on the average, charge carriers do not move with acceleration but with a steady drift velocity. This is because of the collisions with ions and atoms during transit. During collisions, the energy gained by the charges thus is shared with the atoms. The atoms vibrate more vigorously, that is, the conductor heats up. Thus, in an actual conductor, an amount of energy dissipated as heat in the conductor during the time interval delta T is delta W is equal to I V delta T. Equation 31. The energy dissipated per unit time is the power dissipated. P is equal to delta W upon delta T, and we have P is equal to IV. Equation 32. Using Ohm's law, V is equal to IR, we get P is equal to I square R is equal to V square upon R. Equation 33. As the power loss, that is ohmic loss, in a conductor of resistance R carrying a current I. It is this power which heats up, for example, the coil of an electric bulb to incandescence, radiating out heat and light. Where does the power come from? As we have reasoned before, we need an external source to keep a steady current through the conductor. It is clearly this source which must supply this power. In the simple circuit shown with a cell, it is the chemical energy of the cell which supplies this power for as long as it can. The expressions for power, equations 32 and 33, show the dependence of the power dissipated in a resistor R on the current through it and the voltage across it. Equation 33 has an important application to power transmission. Electrical power is transmitted from power stations to homes and factories, which may be hundreds of miles away, via transmission cables. One obviously wants to minimize the power loss in the transmission cables connecting the power stations to homes and factories. We shall see now how this can be achieved. Consider a device R to which a power P is to be delivered via transmission cables having a resistance RC to be dissipated by it finally. If V is the voltage across R and I the current through it, then P is equal to VI. Equation 34. The connecting wires from the power station to the device has a finite resistance RC. The power dissipated in the connecting wires, which is wasted in PC, with PC is equal to I square RC, is equal to P square RC upon V square. Equation 35. From equation 32, thus, to drive a device of power P, the power wasted in the connecting wires is inversely proportional to V square. The transmission cables from power stations are hundreds of miles long and their resistance RC is considerable. To reduce PC, These wires carry current at enormous values of V, and this is the reason for the high voltage danger signs on transmission lines, a common sight as we move away from populated areas. Using electricity at such voltages is not safe, and hence at the other end a device called a transformer lowers the voltage to a value suitable for use. Combination of resistors, series and parallel. The current through a single resistor R, across which there is a potential difference V, is given by Ohm's law. I is equal to V upon R. Resistors are sometimes joined together, and there are simple rules for calculation of equivalent resistance of such combination. Two resistors are said to be in series if only one of their endpoints is joined. If a third resistor is joined with the series combination of the two, then all three are said to be in series. Clearly, we can extend this definition to series combination of any number of resistors. Two or more resistors are said to be in parallel if one end of all the resistors is joined together and similarly the other ends joined together. Consider two resistors R1 and R2 in series. The charge which leaves R1 must be entering R2. Since current measures the rate of flow of charge, this means that the same current I flows through R1 and R2. By Ohm's law, potential difference across R1 is equal to V1 is equal to IR1, and potential difference across R2 is equal to V2 is equal to IR2. The potential difference V across the combination is V1 plus V2. Hence, V is equal to V1 plus V2 is equal to I into R1 plus R2. Equation 36. This is as if the combination had an equivalent resistance R equivalent, which by Ohm's law is R equivalent is equivalent to V upon I is equal to R1 plus R2. Equation 37. If we had three resistors connected in series, then similarly V is equal to IR1 plus IR2 plus IR3 is equal to I into R1 plus R2 plus R3. Equation 38. This obviously can be extended to a series combination of any number n of resistors R1, R2 up to Rn. The equivalent resistance R equivalent is equal to R1 plus R2 plus up to plus Rn. Equation 39. Consider now the parallel combination of two resistors. The charge that flows in at A from the left flows out partly through R1 and partly through R2. The currents I1, I2 shown in the figure are the rates of flow of charge at the points indicated. Hence, I is equal to I1 plus I2. Equation 40. The potential difference between A and B is given by the Ohm's law applied to R1. V is equal to I1 R1. Equation 41. Also, Ohm's law applied to R2 gives V is equal to I2 R2. Equation 42. Therefore, I is equal to I1 plus I2 is equal to V upon R1 plus V upon R2 is equal to V into 1 upon R1 plus 1 upon R2. Equation 43. If the combination was replaced by an equivalent resistance R equivalent, we would have by Ohm's law I is equal to V upon R equivalent. Equation 44. Hence, 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. Equation 45. We can easily see how this extends to three resistors in parallel. Exactly as before, I is equal to I1 plus I2 plus I3. Equation 46. And applying Ohm's law to R1, R2 and R3, we get V is equal to I1 R1, V is equal to I2 R2, V is equal to I3 R3. Equation 47. So that I is equal to I1 plus I2 plus I3 is equal to V into 1 upon R1 plus 1 upon R2 plus 1 upon R3. Equation 48. An equivalent resistance R equivalent that replaces the combination would be such that I is equal to V upon R equivalent. Equation 49. And hence 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus 1 upon R3. Equation 50. We can reason similarly for any number of resistors in parallel. The equivalent resistance of n resistors R1, R2 up to Rn is 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2 plus up to plus 1 upon Rn. Equation 51. These formulae for equivalent resistances can be used to find out currents and voltages in more complicated circuits. Consider, for example, the circuit in figure, where there are three resistors R1, R2 and R3. R2 and R3 are in parallel, and hence we can replace them by an equivalent R equivalent to 3 between point B and C with 1 upon R equivalent to 3 is equal to 1 upon R2 plus 1 upon R3, or R equivalent to 3 is equal to R2 R3 upon R2 plus R3. Equation 52. The circuit now has R1 and R equivalent to 3 in series, and hence their combination can be replaced by an equivalent resistance R equivalent 1 to 3 with R equivalent 1 to 3 is equal to R equivalent to 3 plus R1. Equation 53. If the voltage between A and C is V, the current I is given by I is equal to V upon R equivalent 1 to 3 is equal to V upon R1 plus R2 R3 upon R2 plus R3 is equal to V R2 R3 upon R1 R2 plus R1 R3 plus R2 R3. Equation 54. Tells EMF, internal resistance. We have already mentioned that a simple device to maintain a steady current in an electric circuit is the electrolytic cell. Basically, a cell has two electrodes called the positive P and the negative N. They are immersed in an electrolytic solution. Dipped in the solution, the electrodes exchange charges with the electrolyte. The positive electrode has a potential difference V+, where V+ is greater than 0, between itself and the electrolyte solution immediately adjacent to it marked A in the figure. Similarly, the negative electrode develops a negative potential -V-, where V- is greater than or equal to 0, relative to the electrolyte adjacent to it marked as B in the figure. When there is no current, the electrolyte has the same potential throughout, so that the potential difference between P and N is V plus minus V minus is equal to V plus V minus. This difference is called the electromotive force, that is EMF, of the cell, and is denoted by epsilon. Thus, epsilon is equal to V plus V minus is greater than 0. Equation 55. Note that epsilon is actually a potential difference and not a force. The name EMF, however, is used because of historical reasons and was given at a time when the phenomenon was not understood properly. To understand the significance of epsilon, consider a resistor R connected across the cell. A current I flows across R from C to D. As explained before, a steady current is maintained because current flows from N to P through the electrolyte. Clearly, across the electrolyte, the same current flows through the electrolyte but from N to P, whereas through R, it flows from P to N. The electrolyte through which a current flows has a finite resistance R called the internal resistance. Consider first the situation when R is infinite so that I is equal to V upon R is equal to 0, where V is the potential difference between P and N. Now, V is equal to potential difference between P and A plus potential difference between A and B plus potential difference between B and N is equal to epsilon. Equation 56. Thus, electromotive force epsilon is the potential difference between the positive and negative electrodes in an open circuit. That is, when no current is flowing through the cell. If, however, R is finite, I is not 0. In that case, the potential difference between P and N is V is equal to V plus V minus IR is equal to epsilon minus IR. Equation 57. Note the negative sign in the expression IR for the potential difference between A and B. This is because the current I flows from B to A in the electrolyte. In practical calculations, internal resistances of cells in the circuit may be neglected when the current I is such that epsilon is much greater than IR. The actual values of the internal resistances of cells vary from cell to cell. The internal resistance of dry cells, however, is much higher than the common electrolytic cells. We also observe that since V is the potential difference across R, we have from Ohm's law, V is equal to IR. Equation 58. Combining equations 57 and 58, we get IR is equal to epsilon minus IR, or I is equal to epsilon upon R plus R. Equation 59. The maximum current that can be drawn from a cell is for R is equal to 0, and it is I maximum is equal to epsilon upon R. However, in most cells the maximum allowed current is much lower than this to prevent permanent damage to the cell. Example 5. A network of resistors is connected to a 16-volt battery with internal resistance of 1 ohm as shown in figure. A. Compute the equivalent resistance of the network. B. Obtain the current in each resistor. C. Obtain the voltage drops VAB, VBC and VCD. Solution. A. The network is a simple series and parallel combination of resistors. First, the two 4 ohm resistors in parallel are equivalent to a resistor is equal to 4 into 4 upon 4 plus 4 ohm is equal to 2 ohm. In the same way, the 12 ohm and 6 ohm resistors in parallel are equivalent to a resistor of 12 into 6 upon 12 plus 6 ohm is equal to 4 ohm. The equivalent resistance R of the network is obtained by combining these resistors 2 ohm and 4 ohm with 1 ohm in series. That is, R is equal to 2 ohm plus 4 ohm plus 1 ohm is equal to 7 ohm. B. The total current I in the circuit is I is equal to epsilon upon R plus R is equal to 16 volt upon 7 plus 1 ohm is equal to 2 ampere. Consider the resistors between A and B. If I1 is the current in one of the 4 ohm resistors and I2 the current in the other, I1 into 4 is equal to I2 into 4. That is, I1 is equal to I2, which is otherwise obvious from the symmetry of the two arms. But I1 plus I2 is equal to I is equal to 2 ampere. Thus, I1 is equal to I2 is equal to 1 ampere. That is, current in each 4 ohm resistor is 1 ampere. Current in 1 ohm resistor between B and C would be 2 ampere. Now, consider the resistances between C and D. If I3 is the current in the 12 ohm resistor and I4 in the 6 ohm resistor, I3 into 12 is equal to I4 into 6. That is, I4 is equal to 2I3. But I3 plus I4 is equal to I is equal to 2 ampere. Thus, I3 is equal to 2 upon 3 ampere. Similarly, I4 is equal to 4 upon 3 ampere. That is, the current in the 12 ohm resistor is 2 upon 3 ampere, while the current in the 6 ohm resistor is 4 upon 3 ampere. C. The voltage drop across AB is VAB is equal to I1 into 4 is equal to 1 ampere into 4 ohm is equal to 4 volt. This can also be obtained by multiplying the total current between A and B by the equivalent resistance between A and B. That is, VAB is equal to 2 ampere into 2 ohm is equal to 4 volt. The voltage drop across BC is VBC is equal to 2 ampere into 1 ohm is equal to 2 volt. Finally, the voltage drop across CD is VCD is equal to 12 ohm into I3 is equal to 12 ohm into 2 upon 3 ampere is equal to 8 volt. This can alternately be obtained by multiplying total current between C and D by the equivalent resistance between C and D. That is, VCD is equal to 2 ampere into 4 ohm is equal to 8 volt. Note that the total voltage drop across AD is 4 volt plus 2 volt plus 8 volt is equal to 14 volt. Thus, the terminal voltage of the battery is 14 volt. While its electromotive force is 16 volt, the loss of the voltage is equal to 2 volt is accounted for by the internal resistance 1 ohm of the battery 2 ampere into 1 ohm is equal to 2 volt. Cells in series and in parallel. Like resistors, cells can be combined together in an electric circuit, and like resistors, one can, for calculating currents and voltages in a circuit, replace a combination of cells by an equivalent cell. Consider first two cells in series where one terminal of the two cells is joined together, leaving the other terminal in either cell free. Epsilon 1, epsilon 2 are the electromotive forces of the two cells, and R1, R2 their internal resistances respectively. Let V of A, V of B, V of C be the potentials at points A, B and C. Then V of A minus V of B is the potential difference between the positive and negative terminals of the first cell. We have already calculated it in equation 57, and hence VAB is equal to V of A minus V of B is equal to epsilon 1 minus IR1. Equation 60. Similarly, VBC is equal to V of B minus V of C is equal to epsilon 2 minus IR2. Equation 61. Hence, the potential difference between the terminals A and C of the combination is VAC is equal to V of A minus V of C is equal to V of A minus V of B plus V of B minus V of C is equal to epsilon 1 plus epsilon 2 minus I R1 plus R2. Equation 62. If we wish to replace the combination by a single cell between A and C of electromotive force epsilon equivalent and internal resistance R equivalent, we would have VAC is equal to epsilon equivalent minus I R equivalent. Equation 63. Comparing the last two equations, we get epsilon equivalent is equal to epsilon 1 plus epsilon 2. Equation 64. And R equivalent is equal to R1 plus R2. Equation 65. In figure, we had connected the negative electrode of the first to the positive electrode of the second. If instead we connect the two negatives, equation 61 would change to VBC is equal to minus epsilon 2 minus IR2, and we will get epsilon equivalent is equal to epsilon 1 minus epsilon 2. Epsilon 1 is greater than epsilon 2. Equation 66. The rule for series combination clearly can be extended to any number of cells. Number 1. The equivalent electromotive force of a series combination of n cells is just the sum of their individual electromotive forces. And number 2. The equivalent internal resistance of a series combination of n cells is just the sum of their internal resistances. This is so when the current leaves each cell from the positive electrode. If in the combination, the current leaves any cell from the negative electrode, the electromotive force of the cell enters the expression for epsilon equivalent with a negative sign, as in equation 66. Next, consider a parallel combination of the cells. I1 and I2 are the currents leaving the positive electrodes of the cells. At the point B1, I1 and I2 flow in, whereas the current I flows out. Since as much charge flows in as out, we have I is equal to I1 plus I2. Equation 67. Let V of B1 and V of B2 be the potentials at B1 and B2 respectively. Then considering the first cell, the potential difference across its terminals is V of B1 minus V of B2. Hence, from equation 57, V is equal to epsilon minus IR. V is equivalent to V of B1 minus V of B2 is equal to epsilon 1 minus I1 R1. Equation 68. Points B1 and B2 are connected exactly similarly to the second cell. Hence, considering the second cell, we also have V is equivalent to V of B1 minus V of B2 is equal to epsilon 2 minus I2 R2. Equation 69. Combining the last three equations, I is equal to I1 plus I2 is equal to epsilon 1 minus V upon R1 plus epsilon 2 minus V upon R2 is equal to epsilon 1 upon R1 plus epsilon 2 upon R2 minus V 1 upon R1 plus 1 upon R2. Equation 70. Hence, V is given by V is equal to epsilon 1 R2 plus epsilon 2 R1 upon R1 plus R2 minus I R1 R2 upon R1 plus R2. Equation 71. If we want to replace the combination by a single cell between B1 and B2 of electromotive force epsilon equivalent and internal resistance R equivalent, we would have V is equal to epsilon equivalent minus IR equivalent. Equation 72. The last two equations should be the same, and hence epsilon equivalent is equal to epsilon 1 R2 plus epsilon 2 R1 upon R1 plus R2. Equation 73. R equivalent is equal to R1 R2 upon R1 plus R2. Equation 74. We can put these equations in a similar way. 1 upon R equivalent is equal to 1 upon R1 plus 1 upon R2. Equation 75. Epsilon equivalent upon R equivalent is equal to epsilon 1 upon R1 plus epsilon 2 upon R2. Equation 76. In figure, we had joined the positive terminals together and similarly the two negative ones so that the currents I1, I2 flow out of positive terminals. If the negative terminal of the second is connected to positive terminal of the first, equations 75 and 76 would still be valid with epsilon 2 minus epsilon 2. Equations 75 and 76 can be extended easily if there are n cells of electromotive force epsilon 1, epsilon 2 up to epsilon n and of internal resistances R1, R2 up to Rn respectively. Connected in parallel, the combination is equivalent to a single cell of electromotive force epsilon equivalent and internal resistance R equivalent such that 1 upon R equivalent is equal to 1 upon R1 plus up to plus 1 upon Rn. Equation 77. Epsilon equivalent upon R equivalent is equal to epsilon 1 upon R1 plus up to plus epsilon n upon Rn. Equation 7. Kirchhoff's rules. Electric circuits generally consist of a number of resistors and cells interconnected sometimes in a complicated way. The formulae we have derived earlier for series and parallel combinations of resistors are not always sufficient to determine all the currents and potential differences in the circuit. Two rules called Kirchhoff's rules are very useful for analysis of electric circuits. Given a circuit, we start by labeling currents in each resistor by a symbol, say I, and a directed arrow to indicate that a current I flows along the resistor in the direction indicated. If ultimately I is determined to be positive, the actual current in the resistor is in the direction of the arrow. If I turns out to be negative, the current actually flows in a direction opposite to the arrow. Similarly, for each source, that is, cell or some other source of electrical power, the positive and negative electrodes are labeled as well as a directed arrow with a symbol for the current flowing through the cell. This will tell us the potential difference V is equal to V of P minus V of N is equal to epsilon minus IR. Equation 57. Between the positive terminal P and the negative terminal N, I here is the current flowing from N to P through the cell. If, while labeling the current I through the cell 1 goes from P to N, then of course V is equal to epsilon plus IR. Equation 79. Having clarified labeling, we now state the rules and the proof. A. Junction rule. At any junction, the sum of the currents entering the junction is equal to the sum of currents leaving the junction. This applies equally well if, instead of a junction of several lines, we consider a point in a line. The proof of this rule follows from the fact that when currents are steady, there is no accumulation of charges at any junction or at any point in a line. Thus, the total current flowing in, which is the rate at which change flows into the junction, must equal the total current flowing out. B. Loop rule. The algebraic sum of changes in potential around any closed loop involving resistors and cells in the loop is 0. This rule is also obvious since electric potential is dependent on the location of the point. Thus, starting with any point, if we come back to the same point, the total change must be zero. In a closed loop, we do come back to the starting point and hence the rule. Example 6. A battery of 10 volt and negligible internal resistance is connected across the diagonally opposite corners of a cubical network consisting of 12 resistors, each of resistance 1 ohm. Determine the equivalent resistance of the network and the current along each edge of the cube. Solution: the network is not reducible to a simple series and parallel combinations of resistors. There is, however, a clear symmetry in the problem which we can exploit to obtain the equivalent resistance of the network. The paths AA', AD and AB are obviously symmetrically placed in the network. Thus, the current in each must be the same, say I. Further, at the corners A', B and D, the incoming current I must split equally into the two outgoing branches. In this manner, the current in all the 12 edges of the cube are easily written down in terms of I. Using Kirchhoff's first rule and the symmetry in the problem, next take a closed loop, say ABC, C'E, and apply Kirchhoff's second rule, minus IR minus 1 upon 2 IR minus IR plus epsilon is equal to 0, where R is the resistance of each edge and epsilon the electromotive force of battery. Thus, epsilon is equal to 5 upon 2 IR. The equivalent resistance R equivalent of the network is R equivalent is equal to epsilon upon 3I is equal to 5 upon 6 R. For R is equal to 1 ohm, R equivalent is equal to 5 upon 6 ohm, and for epsilon is equal to 10 volt, the total current is equal to 3I in the network is 3I is equal to 10 volt upon 5 upon 6 ohm is equal to 12 ampere. That is, I is equal to 4 ampere. The current flowing in each edge can now be read off from the figure. It should be noted that because of the symmetry of the network, the great power of Kirchhoff's rules has not been very apparent in example 6. In a general network, there will be no such simplification due to symmetry, and only by application of Kirchhoff's rules to junctions and closed loops, as many as necessary to solve the unknowns in the network, can we handle the problem. This will be illustrated in example 7. Example 7. Determine the current in each branch of the network shown in figure. Solution. Each branch of the network is assigned an unknown current to be determined by the application of Kirchhoff's rules. To reduce the number of unknowns at the outset, the first rule of Kirchhoff is used at every junction to assign the unknown current in each branch. We then have three unknowns I1, I2 and I3, which can be found by applying the second rule of Kirchhoff to three different closed loops. Kirchhoff's second rule for the closed loop ADCA gives 10 minus 4 I1 minus I2 plus 2 I2 plus I3 minus I1 is equal to 0. That is, 7 I1 minus 6 I2 minus 2 I3 is equal to 10. Equation 80A. For the closed loop ABCA, we get 10 minus 4 I2 minus 2 I2 plus I3 minus I1 is equal to 0. That is, I1 plus 6 I2 plus 2 I3 is equal to 10. Equation 80B. For the closed loop BCDEB, we get 5 minus 2 I2 plus I3 minus 2 I2 plus I3 minus I1 is equal to 0. That is 2 I1 minus 4 I2 minus 4 I3 is equal to minus 5. Equation 80C. Equations 80A, B, C are three simultaneous equations in three unknowns. This can be solved by the usual method to give I1 is equal to 2.5 ampere, I2 is equal to 5 upon 8 ampere, I3 is equal to 1 and 7 upon 8 ampere. The currents in the various branches of the network are: AB is 5 upon 8 ampere, CA is 2 and 1 upon 2 ampere, DEB is 1 and 7 upon 8 ampere, AD is 1 and 7 upon 8 ampere, CD is 0 ampere, BC is 2 and 1 upon 2 ampere. It is easily verified that Kirchhoff's second rule applied to the remaining closed loops does not provide any additional independent equation. That is, the above values of currents satisfy the second rule for every closed loop of the network. For example, the total voltage drop over the closed loop BA DEB 5 volt plus 5 upon 8 into 4 volt minus 15 upon 8 into 4 volt equal to 0 as required by Kirchhoff's second rule. Wheatstone bridge. As an application of Kirchhoff's rules, consider the circuit shown in figure, which is called the Wheatstone bridge. The bridge has 4 resistors R1, R2, R3 and R4. Across one pair of diagonally opposite points A and C in the figure, a source is connected. This, that is AC, is called the battery arm. Between the other two vertices B and D, a galvanometer G, which is a device to detect currents, is connected. This line, shown as BD in the figure, is called the galvanometer arm. For simplicity, we assume that the cell has no internal resistance. In general, there will be currents flowing across all the resistors as well as a current Ig through G. Of special interest is the case of a balanced bridge where the resistors are such that Ig is equal to 0. We can easily get the balance condition such that there is no current through G. In this case, the Kirchhoff's junction rule applied to junctions D and B immediately gives us the relations I1 is equal to I3 and I2 is equal to I4. Next, we apply Kirchhoff's loop rule to closed loops ADBA and CBDC. The first loop gives minus I1 R1 plus 0 plus I2 R2 is equal to 0. Ig is equal to 0. Equation 81. The second loop gives, upon using I3 is equal to I1, I4 is equal to I2. I2 R4 plus 0 minus I1 R3 is equal to 0. Equation 82. From equation 81, we obtain I1 upon I2 is equal to R2 upon R1. Whereas from equation 82, we obtain I1 upon I2 is equal to R4 upon R3. Hence, we obtain the condition R2 upon R1 is equal to R4 upon R3. Equation 83A. This last equation relating the 4 resistors is called the balance condition for the galvanometer to give 0 or null deflection. The Wheatstone bridge and its balance condition provide a practical method for determination of an unknown resistance. Let us suppose we have an unknown resistance which we insert in the fourth arm. R4 is thus not known. Keeping known resistance R1 and R2 in the first and second arm of the bridge. We go on varying R3 till the galvanometer shows a null deflection. The bridge then is balanced, and from the balance condition the value of the unknown resistance R4 is given by R4 is equal to R3 R2 upon R1, equation 83b. A practical device using this principle is called the meter bridge. Example 8. The four arms of a Wheatstone bridge have the following resistances. AB is equal to 100 ohm, BC is equal to 10 ohm, CD is equal to 5 ohm, and DA is equal to 60 ohm. A galvanometer of 15 ohm resistance is connected across BD. Calculate the current through the galvanometer when a potential difference of 10 volt is maintained across AC. Solution. Considering the mesh BADB, we have 100 I1 plus 15 IG minus 60 I2 is equal to 0, or 20 I1 plus 3 IG minus 12 I2 is equal to 0. Equation 84a. Considering the mesh BCDB, we have 10 I1 minus IG minus 15 IG minus 5 I2 plus IG is equal to 0. 10 I1 minus 30 IG minus 5 I2 is equal to 0. 2 I1 minus 6 IG minus I2 is equal to 0. Equation 84b. Considering the mesh ADCEA, 60 I2 plus 5 I2 plus IG is equal to 10. 65 I2 plus 5 IG is equal to 10. 13 I2 plus IG is equal to 2. Equation 84c. Multiplying equation 84b by 10. 20 I1 minus 60 IG minus 10 I2 is equal to 0. Equation 84d. From equations 84d and 84a, we have 63 Ig minus 2 I2 is equal to 0. I2 is equal to 31.5 Ig. Equation 84e. Substituting the value of I2 into equation 84c, we get 13 into 31.5 Ig plus Ig is equal to 2. 410.5 Ig is equal to 2. Ig is equal to 4.87 milliampere. Meter bridge. The meter bridge is shown in figure. It consists of a wire of length 1 meter and of uniform cross-sectional area stretched taut and clamped between two thick metallic strips bent at right angles as shown. The metallic strip has two gaps across which resistors can be connected. The endpoints where the wire is clamped are connected to a cell through a key. One end of a galvanometer is connected to the metallic strip midway between the two gaps. The other end of the galvanometer is connected to a jockey. The jockey is essentially a metallic rod whose one end has a knife edge which can slide over the wire to make electrical connection. R is an unknown resistance whose value we want to determine. It is connected across one of the gaps. Across the other gap, we connect a standard known resistance S. The jockey is connected to some point D on the wire, a distance L centimeter from the end A. The jockey can be moved along the wire. The portion AD of the wire has a resistance R centimeter L, where R centimeter is the resistance of the wire per unit centimeter. The portion DC of the wire similarly has a resistance R centimeter 100 minus L. The four arms AB, BC, DA and CD with resistances are S, R centimeter L and R centimeter 100 minus L. Obviously, from a Wheatstone bridge, with AC as the battery arm and BD the galvanometer arm. If the jockey is moved along the wire, then there will be one position where the galvanometer will show no current. Let the distance of the jockey from the end A at the balance point be L is equal to L1. The four resistances of the bridge at the balance point then are R, S, R centimeter L1 and R centimeter 100 minus L1. The balance condition equation 83a gives R upon S is equal to R centimeter L1 upon R centimeter 100 minus L1 is equal to L1 upon 100 minus L1. Equation 85. Thus, once we have found out L1, the unknown resistance R is known in terms of the standard known resistance S by R is equal to S L1 upon 100 minus L1. Equation 86. By choosing various values of S, we would get various values of L1 and calculate R each time. An error in measurement of L1 would naturally result in an error in R. It can be shown that the percentage error in R can be minimized by adjusting the balance point near the middle of the bridge. That is, when L1 is close to 50 cm, this requires a suitable choice of S. Example 9. In a meter bridge, the null points is found at a distance of 33.7 cm from A. If now a resistance of 12 ohm is connected in parallel with S, the null point occurs at 51.9 cm. Determine the values of R and S. Solution. From the first balance point, we get R upon S is equal to 33.7 upon 66.3. Equation 87. After S is connected in parallel with a resistance of 12 ohm, the resistance across the gap changes from S to S equivalent, where S equivalent is equal to 12S upon S plus 12, and hence the new balance condition now gives 51.9 upon 48.1 is equal to R upon S equivalent is equal to R S plus 12 upon 12S. Equation 88. Substituting the value of R upon S from equation 87, we get 51.9 upon 48.1 is equal to S plus 12 upon 12 into 33.7 upon 66.3, which gives S is equal to 13.5 ohm. Using the value of R upon S above, we get R is equal to 6.86 ohm. Potentiometer. This is a versatile instrument. It is basically a long piece of uniform wire, sometimes a few meters in length, across which a standard cell is connected. In actual design, the wire is sometimes cut in several pieces, placed side by side and connected at the ends by thick metal strip. In the figure, the wires run from A to C. The small vertical portions are the thick metal strips connecting the various sections of the wire. A current I flows through the wire, which can be varied by a variable resistance rheostat R in the circuit. Since the wire is uniform, the potential difference between A and any point at a distance L from A is epsilon of L is equal to phi L. Equation 89. Where phi is the potential drop per unit length. Figure shows an application of the potentiometer to compare the electromotive force of two cells of electromotive force epsilon 1 and epsilon 2. The points marked 1, 2, 3 form a two-way key. Consider first a position of the key where 1 and 3 are connected so that the galvanometer is connected to epsilon 1. The jockey is moved along the wire till at a point N1 at a distance L1 from A. There is no deflection in the galvanometer. We can apply Kirchhoff's loop rule to the closed loop AN1 G3LA and get phi L1 plus 0 minus epsilon 1 is equal to 0. Equation 90. Similarly, if another electromotive force epsilon 2 is balanced against L2 into AN2, phi L2 plus 0 minus epsilon 2 is equal to 0. Equation 91. From the last two equations, epsilon 1 upon epsilon 2 is equal to L1 upon L2. Equation 92. This simple mechanism thus allows one to compare the electromotive forces of any two sources. In practice, one of the cells is chosen as a standard cell whose electromotive force is known to a high degree of accuracy. The electromotive force of the other cell is then easily calculated from equation 92. We can also use a potentiometer to measure internal resistance of a cell. For this, the cell electromotive force epsilon, whose internal resistance R is to be determined, is connected across a resistance box through a key K2 as shown in the figure. With key K2 open, balance is obtained at length L1 into AN1. Then epsilon is equal to phi L1. Equation 93a. When key K2 is closed, the cell sends a current I through the resistance box R. If V is the terminal potential difference of the cell and balance is obtained at length L2 into AN2, V is equal to phi L2. Equation 93b. So, we have epsilon upon V is equal to L1 upon L2. Equation 94a. But epsilon is equal to I R plus R and V is equal to IR. This gives epsilon upon V is equal to R plus R upon R. Equation 94b. From equation 94a and 94b, we have R plus R upon R is equal to L1 upon L2. R is equal to R L1 upon L2 minus 1. Equation 95. Using equation 95, we can find the internal resistance of a given cell. The potentiometer has the advantage that it draws no current from the voltage source being measured. As such, it is unaffected by the internal resistance of the source. Example 10. A resistance of R ohm draws current from a potentiometer. The potentiometer has a total resistance R0 ohm. A voltage V is supplied to the potentiometer. Derive an expression for the voltage across R when the sliding contact is in the middle of the potentiometer. Solution: while the slide is in the middle of the potentiometer, only half of its resistance R0 upon 2 will be between the points A and B. Hence, the total resistance between A and B, say R1, will be given by the following expression. 1 upon R1 is equal to 1 upon R plus 1 upon R0 upon 2. R1 is equal to R0R upon R0 plus 2R. The total resistance between A and C will be sum of resistance between A and B and B and C. That is R1 plus R0 upon 2. Therefore, the current flowing through the potentiometer will be I is equal to V upon R1 plus R0 upon 2 is equal to 2V upon 2R1 plus R0. The voltage V1 taken from the potentiometer will be the product of current I and resistance R1. V1 is equal to IR1 is equal to 2V upon 2R1 plus R0 into R1. Substituting for R1, we have V1 is equal to 2V upon 2 R0 into R upon R0 plus 2R plus R0 into R0 into R upon R0 plus 2R. V1 is equal to 2VR upon 2R plus R0 plus 2R, or V1 is equal to 2VR upon R0 plus